Okay, now we are going to discuss the concept of fugacity. The concept of fugacity has a great value for representing the actual behavior of a real gas in the study of chemical equilibria involving gases, especially at a high pressure. We know that for an isothermal expansion, dg, the change in Gibbs free energy, is equal to vdp minus sdt. dg is equal to vdp minus sdt. If the process is isothermal expansion, then we can write dg is equal to vdp, because for an isothermal process dt is equal to 0. Let is equation number 1. And we know that for an ideal gas, PV is equal to RT, or V is equal to RT divided by P, or we can say that dg is equal to RT divided by P into dP, or dg is equal to RT into d ln P. Now this is equation number 2. And this equation number 2 is applicable only in the case of ideal gas. We know that there is no such gas. All gases deviate from ideal behavior. So we have to define a new function f, which is known as fugacity, in such a way that dg is equal to RT into d ln f, and this is equation number 3. So we defined a new function called fugacity. So equation 2 is applicable only to ideal gases, and we have no such gases. Therefore, in order to explain the actual behavior of real gases, we introduced a new term called fugacity. So dg is equal to RT into d ln f, and this equation 3 is satisfied by real gases. If we integrate equation 3, then we can write like this: G is equal to RT into ln f plus C, where C is called the constant of integration. Or if we integrate equation 3 within the limit, then delta G, that is equal to RT into ln F2 by F1. So the change in Gibbs free energy is given by RT into ln F2 by F1. Okay. Similarly, if we consider equation 2 and equation 2 on integration within the limit, we can write like this: delta G is equal to RT into ln P2 divided by P1. P2 divided by P1. We can take this equation as 4 and this equation as 5. And if we compare these two equations, equation 4 and equation 5, we can say that the fugacity is proportional to pressure. Fugacity is proportional to pressure, and it is easy to take the proportionality constant as 1, so that F by P, the ratio of fugacity to pressure, become equal to 1. And we can say that, and this ratio, that is the ratio of fugacity to pressure, become equal to 1 in the case of ideal gas. Whereas in the case of real gases, fugacity and pressure, this ratio will not be equal to 1. So for real gases, we can say that the ratio of F by P will not be equal to 1. അപ്പോൾ നമ്മൾ എന്താ പറഞ്ഞത്, റിയൽ ഗ്യാസിൻ്റെ ബിഹേവിയർ എക്സ്പ്ലെയിൻ ചെയ്യാൻ വേണ്ടി നമ്മൾ കൊണ്ടുവരുന്ന ഒരു പുതിയ ടേം ആണ് എന്ത് പറയുക, ഫുഗാസിറ്റി. ആൻഡ് ഇറ്റ് ഈസ് സിമിലർ ടു ദാറ്റ് ഓഫ് പ്രഷർ. ഇൻ ദ കേസ് ഓഫ് ഐഡിയൽ ഗ്യാസസ് എന്താ പറയുക, ഫുഗാസിറ്റി ആൻഡ് പ്രഷർ എന്ന് പറഞ്ഞാൽ ബോത്ത് ആർ സെയിം എന്നാണ് പറയുന്നത്. ഇനി വി നോ ദാറ്റ് റിയൽ ഗ്യാസസ് tend to behave like ideal gases at a low pressure. So if we decrease the pressure, if the pressure is lowered, then the real gases behave like a ideal gas. Or we can say that limit P tends to 0, F by P, and that is equal to 1. അതായത് ആസ് പ്രഷർ ടെൻസ് ടു 0, പ്രഷർ കുറവായിരിക്കുമ്പോൾ ദിസ് റേഷ്യോ എഫ് ബൈ പി എന്തിനോട് ഈക്വൽ ആവും, 1 ഈക്വൽ ആവും. കാരണം പ്രഷർ കുറവായിരിക്കുമ്പോൾ റിയൽ ഗ്യാസസ് ബിഹേവ് ലൈക്ക് ഐഡിയൽ ഗ്യാസസ്, ആൻഡ് വി നോ ദാറ്റ് ഫോർ ആൻ ഐഡിയൽ ഗ്യാസ് ദ റേഷ്യോ ഓഫ് എഫ് ബൈ പി is equal to 1. So this is about the concept of fugacity. So in order to explain the actual behavior of a real gas, we introduced a new term called fugacity, and it is actually equal to pressure in the case of ideal gases. In the case of real gases, these are two different concepts. They are different.